We're used to seeing vectors as just arrows, or maybe lists of numbers. But what if I told you they have a secret life? Today, we're going to dive deep into the world of linear algebra and uncover the story that every single vector is trying to tell. I love how our source material puts this. Vectors are like nouns. They are the characters in our linear algebra story. It's such a great way to think about it, right? If the vectors are our characters, our nouns, then all the things we do to them, like addition and multiplication, those are the verbs. That's what makes the story happen. And here's our main character, looking exactly how we expect it to, as an arrow. This is its geometric side. It's got a length, we call that its magnitude, and it's pointing in a certain direction. But underneath this arrow costume, it has a totally different identity. So let's pull back the curtain and see what's really going on. We're going to look past the arrow for a second and see what a vector actually is at its core. And there is. That's all it is. When you strip everything else away, a vector is just an ordered list of numbers. And that word ordered is so important. It means the sequence is everything. The vector 1, 2, 3 is a completely different character from the vector 3, 2, 1. This gets us to the vector's dual personality. On one side, you've got the algebraic view, just a list of numbers. But on the other, you've got this dynamic arrow flying through space, the geometric view. Honestly, the real secret to getting good at linear algebra is just learning how to flip between these two perspectives in your head without even thinking about it. Okay, so every vector has two key properties that define it. First is its dimensionality, which is just a fancy way of saying how many numbers are in the list. A 2-number vector lives in a flat 2D world, a 3-number vector lives in our 3D world. Simple enough. Second is its orientation. Is it a column, standing tall, or a row, lying flat? Now, this might seem like a really picky detail, but as you're about to see when we get into coding, it makes a huge difference. Which brings us right here, vectors in practice. Let's take this stuff into the real world with a little Python and see why that tiny detail of orientation can cause some pretty big headaches if you're not paying attention. So in math class or on a whiteboard, this is how you'd see a column vector. It's clean, it's vertical, there's no confusion. This is kind of our perfect, ideal version. Now, when you go to type this in Python, your first instinct is probably to just make a list. But be careful, this is a classic trap. A regular Python list is just a bucket for numbers. It doesn't know anything about orientation, and it doesn't follow the rules of vector math. For what we need to do, it's totally the wrong tool for the job. The right way, the only way really, is to use a library like NumPy. And look closely at the syntax. See those double brackets? That tiny detail is everything. That tells NumPy, hey, I need a proper 2-dimensional array that acts like a real column vector. Seriously, if you take one thing away from this section, let it be this. Getting this syntax right from the get-go will save you hours of headaches down the road. All right, so we know our characters now. It's time to put them on stage and see how they interact. Let's look at the verbs of our story, the operations that really bring these vectors to life. Our first verb is addition. And algebraically, it's about as easy as it gets. You just line up your two vectors and add the matching parts. The first number with the first number, the second with the second, and so on. But here's what that same simple addition looks like geometrically. It's really cool. This shows the tip-to-tail method. You basically just slide the second vector over so that its tail starts right at the tip of the first one. And your answer, the sum, is the new vector that goes from the very beginning of the first one to the very end of the second. Okay, our next action is scalar multiplication. This is just when you multiply a vector by a single number, a scalar. And what it does is it doesn't change the vector's path at all, just its length. So if you multiply by 2, it gets twice as long. Multiply by 0.5, it shrinks to half its size. And if you multiply by a negative number, like -1, it flips a full 180 degrees and points in the exact opposite direction. So now we get to one of the most powerful and honestly most important operations in all of linear algebra, the dot product. On the surface, the calculation looks really simple, but it reveals this incredibly deep geometric truth about how two vectors are related to each other. And the calculation really is just a simple 2-step process. First, you multiply the matching elements from the two vectors, just like we did with addition. Then you just add all of those products together. The result isn't a new vector, by the way. It's just a single number. So we do all that, and we're left with one lonely number. What does it mean? What is that number actually telling us? This, right here, is where the magic happens. That single number is the secret bridge between the algebraic world and the geometric world.
Here it is. The sign of that number tells you about the angle between the two vectors. If the dot product is positive, it means the angle between them is sharp or acute. They're generally pointing in the same direction. If it's negative, the angle is wide or obtuse. But the really, really interesting case is when that dot product is exactly zero.
And this is it. This is the big one. A dot product of 0 means the two vectors are at a perfect 90-degree angle to each other. They are orthogonal. This idea is absolutely fundamental. It gives us a super simple way to test for perpendicularity, and it's used everywhere, from physics to video game design to computer graphics. All right, let's power up. We're going to combine everything we just learned, scaling, adding, and this new idea of orthogonality, and put it all together into one of the most useful techniques in all of linear algebra, vector decomposition. So check this out. This image poses a really interesting question. We've got two vectors, A and B. How would you find the exact point on the line of vector A that is closest to the tip of vector B? This is the whole problem of what we call vector projection. Well, the clever solution is to think about the problem in a new way. Instead of thinking about distance, we're going to decompose vector B. We're going to break it down into two separate, simpler parts. One piece that lies perfectly along vector A, and a second piece that is perfectly perpendicular to it. And this is the beautiful result. The original vector, t, can now be seen as just the sum of its two new components, one part that's parallel to r, and another part that's orthogonal to r. We've successfully broken down a complex vector into two simple perpendicular pieces. This is an incredibly powerful way of thinking. And that leaves us with one last really big question. We've just seen that any vector can be deconstructed or broken down into these simpler orthogonal parts. So, what happens when we apply this exact same idea to the huge, complex vectors that represent our data? What hidden patterns and fundamental structures can we finally start to see?